Christopher Piecuch. He's an assistant scientist at the Woodstoll Oceanographic Institution. Chris got his PhD at the University of Rhode Island in 2016 in oceanography with the focus in physical oceanography. He is now interested in the physics and statistics of coastal and regional sea level variability and change, which is the topic of his talk today. In his research, he combines the use of instrumental observations, proxy records, and numerical simulations, as well as theoretical models. So it's very diverse. And his recent work has focused on understanding how regional sea level is related to large-scale ocean circulation, as well as reconstructing the history of past coastal sea level change. Christopher, thank you so much for joining us today. And we will give you now the presenter ball so that you can talk about your presentation. Thank you very much.
Great. Well, thanks very much, Manu. Thanks also, Kunjamin and everyone else for attending late in the afternoon on a Friday. I'm really excited to have the opportunity to give this talk to you all. So as Manu just said, today we're going to be talking about sea level change. Now, this is a pretty big topic, sea level change. Eventually, what I'm going to do is lead into talking about sea level change along our U.S. East Coast. So from up in New England, where I am, down to the South Atlantic site where you all are. But what I'd like to do to give us a sense of the problem is to start off talking about the global average. So we've probably all heard of global sea level rise. Well, here are the data that support the notion of contemporary global sea level rise. So I'm showing results from a few different recent or semi-recent studies that have all, in different ways, come up with estimates of how much sea level has risen in a globally average sense over the last century or so. So what I'm showing here in this figure is the global mean sea level, or abbreviated GMSL, on the vertical axis. This is shown in units of millimeters. And we're looking back in time over the last 120 years or so. We're going back to the year 1900. And each one of these different curves are the estimate with uncertainties of global mean sea level rise from 5 different recent studies. Now, if you look at these different time series, you can, of course, see various differences between them. Some of them maybe are more noisy, whereas some of them are more smooth. But regardless, whichever estimate you look at, they all show similar first-order behavior in that they're showing a clear global sea level rise signal of, if you were to average the rate of change over the whole century or so, we're looking at a rate of about 1.2 to 1.9 millimeter per year. So again, there's some uncertainty there, but there's a pretty clear consensus that the global average has risen by between 1 and 2 millimeters per year. Again, this is the global average. This is if we were to average the total water volume change of the ocean and normalize that, divide by the ocean's surface area. Okay, so this is a very useful notion for us as climate scientists. It's very valuable for understanding how the ocean interacts with other elements of the climate system. But one complication is that figures like this can be a bit deceptive. And the reason why, and I'll tell you more about this as we go along, is that sea level isn't and never has risen or changed at the same rate everywhere. So if we were to, say, look under the hood of how those 5 studies I showed in the last slide came up with their estimates of global sea level rise on a global average, they're all using data from individual coastal tidal gauge stations. So what I'm showing you here is a global map of the sorts of data that go into those global mean estimates. But each one of the circles you see here scattered over the global coastal ocean represents the location of a coastal tide gauge station, which has been measuring sea level for multiple decades or longer. And to give you a sense of the spatial variation, how sea level rise rates are different from one region to another, at each of these locations I've shaded with a different color, and that color indicates the average rate of rise I get if I take the available data, sea level data at a given location, and just fit a linear trend. So the simplest thing you can do is just fit a linear trend to get an average rate of rise over the multi-decadal to centennial timescale. And what's very clear when we look at a map like this is that the rate of sea level rise, as I said before, isn't the same everywhere. That is, when we look at this map, we see a bunch of different colors. In some regions we see yellows indicating high rates of sea level rise. In some regions we see greens or blues indicating minimal sea level rise or even sea level fall in some places. And moreover, it's not just that the colors change from place to place, that sea level is rising more in one place than another, but that structure is clearly non-random. by that I mean that if you look at the yellows, the yellow high rates seem to cluster together, and the blue low rates seem to cluster together. So we have this very rich spatial structure, okay? And what I'd like to do today, I'm going to focus on a particular region, but I'd like to ask the question is what's responsible for this spatial variation? Why is sea level going up faster in some places, and why is it going up slower or even falling in other places? Now, before I go to the next slide, I want to highlight where we are along the U.S. East Coast. If we look along the U.S. East Coast and consider it in light of all the other global values, we see that we on the East Coast are experiencing some of the highest rates of sea level rise anywhere. So let's zoom in for a closer look. So in this plot, I'm showing a similar one to what I just showed. It's in fact the same exact data, but now we're looking at a much more zoomed in picture of the East Coast, and I've changed the color scale a bit. So this is a region where, again, we're getting higher than global average rates of change. But when we zoom in, we see that even over this smaller region, you have incredible variation in how fast sea level rates, how high sea level is rising. For instance, if you look at this map, perhaps your eye is drawn to the strong yellows and oranges that you see along the Carolinas and the mid-Atlantic coast up through maybe New Jersey. So you're seeing rates of up to 4 millimeters per year over the last century or so in the mid-Atlantic states. But you can contrast that with rates further north along the New England coast, or rates further south along the South Atlantic bight going into the Carolinas, Georgia, and Florida, where rates are substantially lower, things like 2 to 3 millimeters per year. Okay, so there's a clear spatial structure here that rates are faster along the mid-Atlantic coast than to the north along the New England coast, or south along the South Atlantic bight coast. So what I want to do today, the simple question I'm going to ask, and it's a question that many people have asked before over the past couple of decades, is why do you have this spatial structure? What is responsible for sea level going up faster along the mid-Atlantic coast compared to New England and the South Atlantic bight? And before I go any further, I should be clear so we're all on the same page here. I've been, in the past 2 or 3 slides, talking about sea level as measured by a coastal tide gauge. Okay, so we should be clear here that tide gauges are devices that they're affixed to the solid earth. So a tide gauge will measure sea level change either if the sea surface height itself moves up or down, or if Earth's crust itself goes up, uplifts, or subsides and goes down. So when we're looking at sea level from a tide gauge, we're looking at both that sea surface height signal and also potentially a land motion signal. Okay, having clarified that, again, our question here is why do you have this spatial structure? Why are rates higher along the mid-Atlantic coast? Well, let's zoom out for another moment. Before I get into the specifics of the East Coast, I'd like to ask or just discuss what sort of processes in principle can cause sea level to rise at different rates in some places. Because maybe I didn't say this, but this is perhaps maybe a counterintuitive notion. I mean, we know that the oceans are all interconnected. How can it be that sea level is rising faster in some places than others? Well, there are a lot of things that can cause this. So we in this room, with experience in climate dynamics and physical oceanography, we're familiar with some classes of processes. You can imagine things like air-sea heat fluxes. If the ocean takes up more heat, the ocean warms, that seawater will expand thermally and give you sea level rise, possibly at different rates in different places. Also, you can imagine if you have changes in ocean circulation, that is, changes in the way that major ocean currents are moving water volume from one place to another, you could have higher rates of sea level rise in some places compared to others just due to ocean currents redistributing volume around the ocean. So ocean dynamics and air-sea interaction are one class of processes. You can also have melting of land-based ice. So we hear a lot about the melting of mountain glaciers, the ice sheets in Greenland and Antarctica. Of course, that water is melting, running off, and entering the ocean. So in a global average sense, it's increasing the total water mass of the ocean. But, and I won't get into this in too much detail, but due to the changes that causes in Earth's gravitational field and its crust, melting of, say, the Greenland ice sheet and that running into the ocean, that doesn't result in a spatially uniform rate of sea level rise. You might have heard the term sea level fingerprints. That is when the great ice sheets melt, it perturbs Earth's gravitational field, and you actually get non-uniform spatial patterns of sea level rise. So it's another source of regionally varying sea level rates, melting of land ice. You can also have a whole host of other geological processes that can induce vertical land motion. One of the most prominent of which, and I'm going to discuss this a little bit more, is a geological, by which I mean a long-term process that operates over thousands of years, called glacial isostatic adjustment, or as I'll abbreviate it, GIA. So GIA refers to the ongoing response of Earth's gravity field in the crust to the melting of the Laurentide and Fennoscandian ice sheets more than 10,000 years ago. So because the Earth responds in a viscous manner and very slowly, the Earth is actually still responding to the melting of those ice sheets thousands of years ago, and that will have an imprint on sea level. So again, that was sort of a high-level presentation of what kinds of processes in general can cause sea level to change. Let's go back to the East Coast and consider our particular case. Okay, so I'm showing another graph from a paper by Bob Kopp a couple of years ago. This is actually very similar to the plot I just showed, showing the map of the East Coast with the different colored dots showing sea level rise rates. It's just presented in a different way. So what we're looking at here on the y-axis is latitude, going from 28 north, so this is just right about middle of Florida, up to 48 north, which is entering into Canada, so the whole East Coast. And on the x-axis is shown the rate of sea level change over long time scales, century or longer. The different blue symbols are the values you get from those tide gauge records that I showed you before, where the dots are showing the median, and the dashes, the different dashes are showing different measures of uncertainty. Okay, and again, we see that structure I pointed to before, where if you look at the mid-Atlantic, say between 37 and 39 north, between Portsmouth, Virginia, and Atlantic City, you see the highest rates of rise. And that rate of rise drops off rapidly as you move to the north, towards Maine. It also drops off rapidly as you move south to the Florida coast. That's the blue. Green is the rate of long-term, multi-century sea level rise as inferred from paleoproxies derived from radiocarbon-dated salt marsh sediment. So this is giving us a longer-term picture of sea level rise at salt marsh sites up and down the East Coast. That's what's shown in green. And finally, the red circles they're actually not observations, it's a model estimate. So the red circles indicate the rate of rise expected from a simulation of that glacial isostatic adjustment process that I mentioned a moment ago. Okay, so we have three different data streams, if you will, here. Now, on a first glance, the red, the blue, and the green are, in a qualitative sense, telling a similar story. All three of them show spatial variation in sea level rise rate. It's going up faster in some places than others. And they all, again, to the first order, are suggesting that the fastest rates are happening somewhere on the mid-Atlantic coast. The red and the green suggest maybe that highest rate is happening somewhere around 40 north, so New Jersey, New York area. Whereas the tide gauge data in blue are suggesting, no, maybe it's a bit further south along the Virginia and Maryland coast where you get the highest rates of change. Okay, but they're all saying that the mid-Atlantic has the highest rates of change. But again, as I hinted to a moment ago, the closer you stare at this figure, the more differences may or may not present themselves. For example, if we look between about 37 and 39 north, we see that those red circles seem to fall outside the uncertainty bounds of the blue dashes from the tide gauges. Now, it's difficult to say based on this plot whether or not that represents anything significant. I mean, the GIA results are given just as point estimates, there's no uncertainties. So it's unclear that if you were to consider uncertainties in the GIA model, then they would maybe overlap. Similarly, there's this stray green square at maybe 38 north. So this is near Portsmouth. That green square from the salt marsh sediment also falls outside of the blue error bounds, but it could be that one site is something of an outlier. Okay, so I'm sort of giving some examples of the sorts of questions that we can ask ourselves looking at plots like this. You know, to what extent are these different data sets telling us a common story, and to what extent are they telling us different things, and what's the interpretation? Okay, so the sorts of questions that I've been running through with you for the past couple of minutes are questions that people have asked before, and as a result, people have come up with a lot of different hypotheses regarding what's causing these spatially variable rates of sea level rise on the coast. Almost universally, based on plots like the one I showed you, people think that the glacial isostatic adjustment process is at least contributing and is important. But there's uncertainty in terms of just how important. Can glacial isostatic adjustment explain the entirety of that spatial variation, or only a part? And if it's only a part, then what else is causing sea level rise at spatially varying rates? And in that sense, people have suggested any number of things. So there's been a whole class of papers that suggest maybe also changes in ocean circulation are involved. If you imagine perhaps strengthening or weakening or maybe a northward or southward shift of the Gulf Stream, that could potentially have an influence on coastal sea level, and different people have suggested things along those lines. You could also, as I mentioned a moment ago, have melting of something like the Greenland ice sheet, which is going to have a spatially variable rate of sea level rise. There have been a couple papers that have suggested surface mass distribution and melting of ice to contribute, and also more local processes, things like the sediment compaction associated with withdrawing groundwater or other resources, even the gravitational signature associated with damming. All of these things come together in what I call a zoo of hypotheses that have been collected over the past, say, 3 decades, and people saying different things about what may or may not be contributing to sea level rise on the East Coast. You may ask yourself, are all of these processes important? Are some important but not others? Are these different hypotheses, do they contradict one another? Well, it's difficult to say, and the reason why is that all the data sets that we discussed, tide gauges, salt marsh sediment records, these GIA models, even GPS measurements, which I'll get into in a moment, they're all very error-prone and uncertain data sets. And the uncertainties in these data sets tend to get swept under the rug when people perform studies like this. For example, we've been talking about the GIA models. There are a couple publicly available GIA models that people tend to download and use when interpreting tide gauge records, but in fact, these models are highly uncertain, but the models are usually provided without errors. So to give you a sense of how uncertain they are, we ran a couple hundred different GIA model solutions. And so what the GIA models are doing, again, they're simulating the response of the Earth to the former loading of the ice sheet. So you have to input to your model the evolution in space and time of where the ice was and when. You also have to tell your model how thick Earth's lithosphere is and how viscous the mantle is. So these parameters, sort of the surface forcing, if you will, and then these internal Earth parameters determine how the Earth will respond. But these parameters themselves, viscosity, the lithosphere thickness, the ice history, they're all uncertain. So we ran a couple hundred model runs where we varied the ice history, we varied the mantle viscosity, we varied the lithosphere thickness, all within reasonable bounds to get some crude measure of uncertainty. And we just, here in this plot, took the standard deviation. And what you see is, especially along the northeast coast, you see these very bright yellow values. So this is standard errors, if you will, or standard deviations on the order of 1 millimeter per year. This is a very large uncertainty relative to the signals we're trying to explain. The signals we're trying to explain are on the order of a couple millimeters per year. So these uncertainties in GIA models are potentially very important, but they're almost never taken into account in studies of East Coast sea level. Not to rag on the models too much, the data are also very messy. So I'm showing some examples of tide gauge sea level records that are the foundation of all studies of modern East Coast sea level rise. So I've shown 5 time series here. They're all showing sea level in meters. This is on the y-axis. I've imposed an arbitrary offset, so we're up near 7 meters. And time along the x-axis, going back to the early 1900s. Each color refers to a different location, which I've indicated in the legend to the top left of the figure. So if we look at these, we see that there are some features that all time series have in common. They all show more or less linear or maybe even nonlinear rate of rise over the record. But superimposed on that more or less linear or long-term rate of rise are these interannual to decadal fluctuations. Okay, and if we were to compare one colored curve to another, we can say, well, there seems to be correlation. When one curve is fluctuating, the neighboring curve seems to fluctuate the same way. I should say that all these tide gauges are very close to one another. They're all along the New England coast, either in Massachusetts or Maine. So they show gross first-order similarities, but the closer we look, the more we notice differences. For instance, if we look at the green curve from Portland, Maine, and we sort of trace with our eye the linear rate of rise, it rises slower than any of the other curves. So the rate of rise isn't the same everywhere. Moreover, if we keep our eyes on this green curve from Portland and we look at the 1960s and 1970s, there are these very large fluctuations in sea level at Portland on the order of 10 centimeters that aren't really seen at the other sites. So while we have this qualitative consistency between all of the time series, there are these very important quantitative differences. On top of that, we see that the different time series start at different points. The Portland green time series starts before 1920, but the blue time series, which is from Nantucket Island, that doesn't start till after the 1960s. And if we look between those points, there are a lot of gaps when you don't have data available. So if we're going to really rigorously try to answer the question, what's causing variable rates of sea level rise, we need to somehow come up with a way to accommodate all this noise and all these gaps. Added to that, again, we're bringing different data sets to the fore here. We're looking at coastal tide gauge stations. We're also taking these sediment core records from different salt marshes, as I'll explain in a moment. We've also used GPS station measurements, which are giving us measurements of that vertical land motion or crustal motion. The problem is that these different data sets aren't all in the same location. They're very heterogeneously distributed. I'm trying to show here in the map. So all the blue dots are locations where tide gauges are. The orange dots are where you have a GPS location, and yellow is where you have a salt marsh from which a sediment core has been extracted to reconstruct sea level over the last 2,000 years. So you have a very heterogeneous distribution. In some places, the data are clustered densely, like along the Mid-Atlantic and Chesapeake Bay area. In other areas, the data are very sparse. So for example, if we look at South Carolina, Georgia, and Florida, there's only one salt marsh along the whole part of that coast. Okay, so they can be clustered or they can be very sparse. And the different data types aren't all in the same place. That is to say, where I have a tide gauge measuring sea level, I don't necessarily, and usually don't, have a GPS station measuring vertical land motion. The stations can be separated by tens, if not hundreds of kilometers. So coming up with some rigorous way to account for the different locations of the different data sets is going to be an important part of our analysis. I've also given here these black outline squares, which is what I wish we had, which was all the different data sets, all on a regular lat long grid. As we downloaded a reanalysis data set. It's always nice to work with easy gridded data sets, and that's what we're actually going to shoot for today. I'm going to try to take all these different data sets I've been describing and create a regular gridded data set that tries to account for all of these uncertainties that I just mentioned, uncertainties in the models, uncertainties in the data. So I'm just going to review here. These are the data sets that I'm going to bring together to answer the question, why does sea level rise at different rates on the US East Coast? So we're going to use sea level records, similar to what I just showed you. I showed you 5 sea level records from tide gauges a couple of slides ago. We're going to use 53 total tide gauge records, which I'm indicating in blue, up and down the East Coast from Atlantic Canada to southwestern Florida. I'm going to take estimates of vertical land motion, so this is your rates of crustal uplift or subsidence from 42 different GPS stations, which I'm showing here in orange. I also have, there are 23 salt marshes up and down the coast, which I'm showing here in yellow, from which we have over 160 proxy reconstructions of sea level, that is, pairs of sea level and age going back in time of how high sea level was so far back in the past, which will give us an observational estimate geological rates of change over the last 2,000 years. And finally, I alluded to this a moment ago, we have over 200 GIA models, which we've run by varying the ice history. So this is essentially the surface forcing, if you will. And we've also had used about 72 different combinations of varying the lithospheric thickness and how viscous the upper and lower mantle are. So those are our different data sets. Now the challenge, as I've kind of been leading us up to this whole time, is how do we deal with this? What we have is this problem that is just laden with all these levels of uncertainty. It's what I want is a mathematical or analysis framework that is able to coherently cope with all those uncertainties. And I don't want to wade too deep in the waters of methods here. I just want to give you enough of a sense of the basic philosophy of what we're doing. So the method I'm using here is it's called Bayesian data analysis or hierarchical modeling. And the problem is this, if we want to abstract for a second. So the problem we have is that we have some observational data, let's call it here Z. We have some observational data that is imperfect for whatever reason. It could be noisy, it could have gaps, it could be not at all the space and time locations that we want it. It's an imperfect data set Z, but it's measuring this process or physical variable we're interested in. We'll call that physical variable Y. In our case, that's sea level, okay? And we have the data Z, we have the process or variable Y, and the relationship between Y and Z, that is how the observation relates to the process, and how the process itself evolves in space and time, how sea level, in this case, behaves in space and time, are going to be governed by a set of parameters. I'll call them theta. We don't know the numerical values, but the things we're talking about here are things like the instrumental error variance of the tide gauge measurement, for example, or maybe the time scales of variation of sea level, maybe the spatial scales. There are all these parameters that describe the process and its relation to the data that I don't know. And this boxed equation is, in a schematic sense, it's basically showing us Bayes' theorem, but it's giving us a way to proceed with this problem. Again, what I want in the end is what's to the far left of this equation. Set in some sort of mathy terms, I'm trying to infer what's called a posterior probability distribution. In the simplest sense, what I want to know how sea level behaves on a regular space-time grid that I showed you before. And I also want to know all these parameters I just mentioned, things like spatial scales, time scales. And I want to come up with estimates of these things, the process and the parameters, based only on the messy, noisy data that I have, Z. So that's what the posterior is saying. It's what's the probability of the process and the parameters given the data Z. And as I said a moment ago, this is expressing Bayes' rule there. So Bayes' rule allows us to take what is this very complex problem with all this uncertainty. There's uncertainty in the measurements, there's uncertainty in the process, and it allows us to break it down into more manageable chunks. Okay, so let me walk through the right-hand side. So this thing I'm interested in on the left, I write in terms of, on the one hand, a process level. You can think of this as the physics. How does sea level, in this case y, how does y behave given these parameters, these time scales, these length scales? So what I'm going to do is write down a process level equation that describes how sea level evolves in space and time. So let me go a couple slides back here to tell you what I mean. So we're looking at these tide gauge data of sea level. By looking at these data, we have some intuition for how sea level behaves in time. Like I said before, it has a trend, but it also has this interannual to decadal noise. And there's also some spatial correlation. We pointed those things out before when we were on this slide. So I'm going to take those notions that we can visually see in the data, and I'm going to formalize those in terms of some equations that say that sea level has both spatial and temporal correlation. So that's what I'm talking about when I talk about writing a process level equation. Moving on to the orange, we have, separate from the process, we have what I'm calling the data level or the measurement model. How do these gappy and biased tide gauge measurements, for example, relate to the process, sea level? Okay, so I'm going to write some measurement model that relates the observation to the process itself. And it's going to account for gaps, again, any instrumental errors, biases, things like that. And finally, we have what's called the prior level or the parameter level. I've talked about this process or physical level, this data or measurement level. So I've written down these equations and these different parameters appear, but it's at the prior level that I specify how well I do or do not know the numerical values of those parameters. Okay. So what I do, I write down those equations, and Bayes' rule gives me a way to evaluate that. Again, I hesitate to get into any of the real nitty-gritty details, but suffice it to say, I write down this model, I evaluate it numerically using Monte Carlo methods, and what comes out isn't just summary statistics, things like means and variances. What we have is a whole ensemble, a fully probabilistic ensemble of solutions that has thousands of members. Each of those members is equally likely given the data, and by having these thousands of ensemble members, it allows us to do very rigorous statistics, like I'll show you in a second, which is really nice given all the difficulties I described before. So I'm going to end with maybe 2 or 3 slides here showing you what the model looks like compared to the data. So on the left here, I'm showing you what I've already shown you. So the left is showing the rates of observed sea level rise up and down the East Coast from tide gauges. Again, we have the problem of the heterogeneous distribution of the data. There are more data in some places than others. There is some apparent large-scale structure in the data where we thought that perhaps the rates were higher along the mid-Atlantic coast, but there is some noise, maybe some outliers near Cape Cod and southeast Florida. On the right, I'm showing the same physical quantity. This is the rate of the sea level rise between 1900 and 2017, but it's from this Bayesian model that I've roughly described, where I've assimilated all these different data sets. And a couple things jump out at you. So I'm just showing the median, the best estimate model solution. One thing is that as I hinted before, I'm able to produce a gridded product. We have the solution on a regular grid up and down the East Coast, so you don't have the heterogeneous distribution as you have the data. And also, you can see that the spatial structure is much more apparent. It's very clear to see that these high rates of sea level rise, near 4 millimeters per year, are occurring along the mid-Atlantic coast, say near Virginia and Maryland, and that those rates drop off fairly uniformly as we go north to New England and south to Florida. That spatial structure is much more apparent in the Bayesian solution than it is in the observational data. Here's another contour of the solution, if you will. So again, we're looking at rates of sea level rise. I'm not showing a map now, but similar to Bob Kopp's figure from before, I'm showing you things as a function of latitude. So we have latitude along the East Coast on the y-axis. So we're going from 25 south, this is the southern tip of Florida, up to 45 north, which is the US-Canada border. And I'm showing rates of sea level rise on the x-axis in millimeters per year. And I'm showing 3 different colors here. So blue is the full relative sea level field that I've been discussing so far, that I also showed in the previous slide. This is the total rate of sea level rise. Earlier in my talk, I said that relative sea level represents the difference between the sea surface height and Earth's crust. So what I've done here is I've tried to, taking that into account, I've decomposed the total blue relative sea level data into its sea surface height and vertical land motion, crustal motion components. And I should say that there's the reason why the orange curve is sort of facing in the negative direction is a vertical coordinate issue. If you have positive vertical land motion, that means your land is uplifting, which means that you have a negative sea level rise. So there's this factor of -1 in the vertical coordinate that makes the vertical land motion negative. So with each of these three colors, blue, yellow, and red, I'm showing a few different things. So the thick curve for each of these colors is the mean estimate. The shading is the 95% credible interval. And as I said a moment ago, we don't just have summary statistics. We have an ensemble of thousands of members. So the thin squiggly curves for each color are, I've just randomly chosen 2 ensemble members to give you a sense of what the individual ensemble members from which I'm computing the statistics look like. So to summarize, if we look at the blue, we see the behavior that I've talked about before. The blue is showing that the highest rates, on the order of 4 millimeters per year, are happening around 36 or 37 north. So again, this is around Virginia and Maryland. And if we go north to 45 north or south to 25 north, those rates fall off. And we see that if we look at the different components, the SSH in yellow or the vertical land motion in orange, that pattern of variation, high rates in the mid-Atlantic, low rates elsewhere, is almost perfectly mirrored in the vertical land motion. That is, if we look at the orange curve, we see the strongest sinking, the strongest subsidence at the same latitudes of 36, 37 north, whereas we have less strong rates of subsidence to the north and to the south. So what this is telling us is that the primary reason that we have variable rates of sea level rise on the East Coast is because the land is sinking at different rates. That is, the land is sinking just about up and down the whole East Coast, and it's sinking the fastest just north of Cape Hatteras along the Virginia and Maryland coast. If we look at the yellow curve, this represents the sea surface height change. It's much more uniform, going from more north to south. That is, that sea surface height change is not contributing very much to the total variation in the relative sea level curve. So we've established here that most of that spatial variation is due to vertical land motion. We can get even more insight if we do sort of a complementary or a different decomposition of the data. Remember, I've been talking about this GIA process, and that we have assimilated different GIA models. We're able to break down the total sea level curve, which again I'm showing in blue. So the blue curve again is that total relative sea level. It's identical to what I just showed in the previous slide, but rather than breaking the relative sea level down into sea surface height and vertical land motion, I'm doing something different. I'm breaking it down into the sea level contribution to GIA and the contribution due to everything else. So the non-GIA can be anything like ocean dynamics, melting of ice sheets in the present day, anything that's not GIA. So again, with the blue, we see those higher rates along the mid-Atlantic, lower rates to the north and south, and in a qualitative sense, the orange curve, which is due to GIA, even though it's offset from the blue, that is, the orange curve is about 2 millimeters per year lower on average than the blue curve, the spatial changes are very similar. That is, if we look at the orange curve, the fastest rates are occurring around 37 north, same place where the highest sea level rates are happening. And similarly, if you look at the orange curve and move to the north, to the Maine coast, or if you move to the south, towards Florida, those rates fall off. So what we're seeing here is that it's the GIA process that is contributing an important part to that total sea level variation. If we look at the yellow non-GIA component, it has much less spatial variation. It has much less spatial variation, but not no spatial variation. If we look at the yellow curve, the yellow shading, we see that there actually is some structure such that rates are about 1 millimeter a year higher to the south along the South Florida coast than they are to the north along the Maine coast. That is, if you were to run your eye from top to bottom on this graph, the yellow curve increases by about 1 millimeter per year. Okay, so there is some spatial structure there. We're not really sure what that is, actually. We hypothesized that, if you remember before, we talked about how the melting of ice on land has a geographic fingerprint associated with that. It turns out that, again, I won't go into too much detail here, but an increase of the rate from north to south is actually consistent with the melting of ice at northern latitudes. So these are some quick results from a recent study we published trying to understand why sea level rates are spatially variable along the East Coast, and trying to sort of resolve what was a long-standing conundrum in the literature. So to summarize, we applied this Bayesian data analysis observations to proxies and to model solutions. We found that the GIA, or glacial isostatic adjustment process, is the most important first-order control on the pattern of sea level rise that we've observed in tide gauges. As I just showed in the previous slide, there are possibly also second-order effects that might be due to mass redistribution, that ice melting part that I talked about. An important result that I don't have really much time to go into today is that these results are actually inconsistent with a major role for ocean circulation. There have been studies, I cited some of them at the beginning of my talk, that suggest that changes in ocean circulation might have caused sea level change at the coast, but these results are in fact not consistent with the picture that would result from a circulation change. So with that, thank you very much for your attention. I'm happy to take any questions.
Thank you. Thank you for your great presentation.
Thank you. Yep, go ahead, Kunjamin. Yes, you're the conversation lead. Go ahead.
Are there anyone who wanna ask something about this presentation? Okay, I have a question.
Yeah, sure.
First of all,